Today we want to look at calculating some limits using some algebra again, like we were doing yesterday. We want to remind ourselves of some things about rational functions that we know that will be useful. And we want to see how we could use that to calculate limits. Let's begin with the limit we calculated yesterday. We had the limit as x approaches 1 of 2x squared minus x minus 1 over x minus 1. And we found out that that was equal to 3. We got there by noticing that the numerator was factorable and we were able to cancel out the x minus 1. So notice that I used the equal signs in between all these because in between these two steps, we are evaluating a limit. The limit of the rational function is the same as the limit of the polynomial. The only time the rational function is not equal to the polynomial is when x is equal to 1. But when we're calculating limits, we don't care what's going on when x equals 1. We care what's going on when x is near 1. So these two functions are not equal when x equals 1. So these two functions this rational function is not equal to the polynomial when x is equal to 1. But we're calculating a limit, so we only care what's happening near 1, not at 1. So the rational function is not equal to the polynomial when x is equal to 1, but we're calculating a limit. So we're only concerned with values close to 1, not 1 itself. We're only concerning with values close to 1, not at 1. That's why it's okay for us to just cancel out the x minus 1 and use the resulting polynomial to calculate the limit. The polynomial is continuous at x equals 1, so we just plug 1 into the polynomial. We get to evaluate the polynomial at x equals 1, because as we observed before, if a function is continuous, then the limit is equal to the value of the function. And the polynomial 2x plus 1 is continuous everywhere. That's the kind of thinking that we're using when we're using this algebra stuff to simplify and then evaluate. Remember, we want to do the simplest thing. We're hoping that the function is continuous at the point we care about where we're evaluating the limits so that we could just plug that value into the function. But since this is a math class, we never pick the value where the function is continuous. Otherwise, there wouldn't be much of a problem. So we emphasize by always picking bad values for the function. So we have to do something. Any questions? Is everybody okay? So we know that since we're only concerned with values near the x approaches c, we can simplify things and try to cancel out denominators. I didn't leave space for my next comment. So let's look at this next limit. We have x squared minus 1 over x squared minus 2x plus 1. Clearly, I didn't want to work very hard on my factoring, but we're going to factor the numerator and denominator to see if they have anything in common that we can cancel out. That's the strategy that we picked up yesterday. Let's see if it helps here. So we're going to apply the same strategy. I'm going to try to factor the numerator and denominator. I'm still taking a limit as x approaches 1. The denominator factors into x minus 1 times another x minus 1. And the numerator factors into x minus 1 times x plus 1. Like I said, I didn't want to work really hard on the factoring, since factoring is not the point of the problem. So in this case, we can cancel out a factor of x minus 1, but it doesn't really help us because there's 2 factors of x minus 1, and we can only cancel out one of them. So we are able to cancel out a factor of x minus 1, but there were 2 down there causing problems. Here we are only able to cancel So good news, we were able to cancel one of the factors of x minus 1. Bad news, there is still a factor of x minus 1 in the denominator, so I can't plug in. So since this is a rational function, knowing that we have still a value that makes the denominator equal to 0, that means we have a vertical asymptote in our graph. And that means the function, that means the limit does not exist. Want to be careful with our equal signs. When you use an equal sign, you're saying these 2 things are the same. So I don't want to say equals does not exist because that looks weird. I'd have to be in a really foul mood to take off points if you're like, oh, equals DNE. That would be kind of a jerk move on my part. And then eventually I'd look at them, I go, nah, that's pretty harsh, man. Why don't you calm down, have another sip of coffee, and put those in. But it's not something that we should encourage. It's the same thing with saying like the limit as x goes to 0 of 1 over x squared equals infinity. I'd have to be kind of in a cranky mood to be taking off points for that, because it's only not technically correct. We're communicating the right idea. The function is off towards infinity, but to say it equals infinity is bad form. Trying to think of other things that are bad form, but it's bad form. It's like sending an email in all caps, but no one does that anymore, do they? Unless they are actually shouting. I had a friend that emailed in all caps. I'm like, oh, dude, why are you shouting? And he's like, oh, because I'm always shouting. And I'm like, oh, fair. You know what I mean? Yeah, it makes the email look angry. I've had students that write in all caps, and if you write in all caps, you are incorrect. If you write by hand in all caps, you are incorrect. You're in a math class now. Math is case sensitive. The function little e to the x is a function. If you write a capital E to the x, I might call, what function is this? I'm really a dick about it, so switch, turn caps lock off, calm down, lowercase e. Same thing with sine, cosine, and tangent. Don't be like, write that in all caps. It's not supposed to be all caps. Don't be shouting your math at me. So here we were only able to cancel one factor of x minus 1, so we still have a vertical asymptote. So there's still a vertical asymptote at x equals 1. This is reminding us of some stuff about rational functions. A factor that makes the denominator a 0, a factor that makes the denominator equal to 0 will produce a vertical asymptote unless we can cancel it out, in which case it produces a whole. In the previous example, the recall example, we were able to cancel the x minus 1, so there was a whole at 1. In the second example, we were not able to cancel all the x minus 1, so there's a vertical asymptote at x equals 1. Those are the two things that happen when the denominator is equal to 0. Any questions? How's everybody okay? Everybody remember your rational functions? There's no quiz today, so you can just be like safely, yeah, totally. Absolutely. Two things could happen. Vertical asymptotes, whole in the graph. You might not remember it from high school because in high school you can't talk about this. Because it's a day of rational functions, and in a high school classroom, you cannot be talking about graph holes and asymptotes, which is how mathematicians cuss each other out in traffic. One mathematician cuts the other one off, and the first mathematician will be like, oh, graph hole, and the other one's like, oh, asymptote. But then they realize they're both mathematicians and then high-five each other. No, I don't think so. I'm not sure if what I remember is true or not. So we dealt with the first two problems with factoring, and this last one, this is not the last one. It'll be like, oh, good, we're almost done with examples. You mean last one for the semester? It's like, oh, no. This third one, now everybody's sad. This third one has a radical in it. So it's like a rational function, but then there's that square root, messes everything up. It's a radical function. I know you're looking at it, it's like, oh, not that radical, but it's got this 1/2 exponent in it. So the radical function. We have ways of dealing with this. In fact, we're going to use the same strategy. I'm going to factor and cancel. Notice the numerator is x minus 4, and the denominator is the square root of x minus 2. So this I can factor in a useful fashion. The only reason I'm going to be doing this is that the numerator has an exponent of 1, and the denominator has an exponent with a 1/2. The denominator exponent is half the numerator. It's also a -4 and a -2. So if you're looking at this and thinking, Leach, that's super contrived. This is not going to happen out in the wild. I'm like, oh, no, absolutely not. This is absolutely super contrived to make a point. I want to expand your thinking about factoring. So because we're in a math class, we can say, well, isn't this convenient? First, we're going to notice that we can't plug in the 4 because the denominator goes to 0. The numerator goes to 0, but it's okay for numerators to be 0. Denominator equals 0, bad. Numerator equals 0, okay. We've got a bad value with this 4. There's a vertical asymptote or a hole in the graph. One of those two things. So right now we got to determine if it's a graph hole or an asymptote. If I can cancel out the square root of x minus 2, which you know I'm going to be able to do because that's the point of the problem. If I'm able to cancel out the square root of x minus 2, then we'll have a graph hole. If we're not, then it's an asymptote and the limit doesn't exist. So let's find out. let's find out what we already know. The numerator we're going to factor as the difference of squares. X is the square root of x squared. Technically, it should be absolute value of x if I'm going to play that game, but I need to get all the way off my back about that. So the numerator is going to be the square root of x minus 2 times the square root of x plus 2. And the denominator is going to stay square root of x minus 2. So if we expand our ideas about factoring, we see we can factor out the we can cancel out the denominator. So now when we plug in x equals 4, the square root of 4 is 2. 2 plus 2 is back to being 4. And so we've got a sneaky way of dealing with this problem. We can expand our thinking about what's factorable and factor not over integer exponents, or even worse, positive integer exponents, but also now fraction exponents. Any questions? Incorrect. There's a big question here. What if we didn't notice this? What if we saw this radical and didn't immediately think of factoring because we're not a math teacher coming up with examples for our class to go over? What if we looked at this and said, ooh, radical in the denominator, what can we do there? So set the Wayback Machine to algebra. What do we do with radicals in the denominator? By square root of x plus 2. What's that process called? Does anybody remember? The square root of x plus 2 will be the conjugate of that. And this process is called, anybody remember? It's where we make something rational from irrational. That's okay. Almost everybody forgets the names of things. It's called rationalization. We have names. Did someone have it? Oh, I didn't hear. I'm sorry. So I'll retcon some points for you. So I'll do like my old Professor Electron Don Pershing. You get an A. So what if the radical distracts us from the factorable? So what if the radical distracts us from the factorable or from factoring? Then we just do radical stuff. We rationalize the denominator. This is the usual move when we see radicals in the denominator. When we want something to happen, in a land of calculators, having an answer that says 1 over the square root of 2 is perfectly valid. It's perfectly okay to have radicals in the denominator. There are reasons it wasn't considered simplified for a long time, but now that we have massive computing power and everybody has a calculator, it's fine to leave radicals in the denominator. But sometimes these moves come in handy. It's like, oh, I need something to happen in this problem, so I'm going to rationalize the denominator. So it'll look like this. We'll take the limit as x approaches 4 of x minus 4 over root x minus 2, and we will multiply by the conjugate of the denominator. And this conjugate was easy to spot because it was a square, so no problem here. What this does for us the numerator, I'm going to leave multiplied out. Or sorry, factored out. But when I multiply out the denominator, I'm going to use the difference of squares in reverse. And I'll have the square root of x times square root of x is x. The middle two terms will cancel out. -2 times +2 is -4. So I end up with an x minus 4. At this point, we can see, dude, x equals 4 is still a bad value, but now the x minus 4 will cancel out because the problem was so contrived. And the answer is still 4. Moreover, the limit that we need to get there when we evaluate the resulting radical function is the same. Any questions? It raises a question, which is best? The best method is the one that you happen to think of. So some of you notice, some of you see the radical and say, radical in the denominator, I'm going to rationalize that denominator. And if some of you are like, I have a sneaky way. I'm going to factor it. Any questions? This is why teaching math is like being a dungeon master in a tabletop role-playing game and not a programmer in a computer game. Programmer computer game has a limited list of things that you could do to solve the problem that's put in front of you. But if you're a dungeon master with human players that can kind of do anything that they want, you have to be prepared for some weird solutions to the problems you put in front of them. I mentioned that because my players come up with weird solutions to things. The more time I give them to think about a problem, the weirder the solution gets. If you just spring something on them, sometimes I'll just like, let's just roll initiative. But if I present them with a problem and a cliffhanger, then I know I'm in trouble the following week because they're going to spend a week plotting. It's like, wait, how did he describe this keep? How big was it again? And he said there's a creek running through it, didn't he? And we have the spell control water, don't we? See, if they're doing that at the table right in front of me, then I'm like, oh, I see where this is going. But if I just leave them with the cliffhanger, we sit down next week, and they all have this grin on their face. And I go, oh, wow, my guys are in trouble. Right, D&D, fifth edition. I started in AD&D, for those of you, I go way back. My first gaming console was an Atari 2600. That's how old I am. And my first edition of D&D was first edition of D&D. Before they even called it first edition, they just called it D&D. Incidentally, if you get a hankering for some old school gaming and you want to grab some old D&D and play that, don't. It is a bad system. Third edition is where they actually designed a system to, like, what's it called? Operate. And then fifth edition is a refinement of that. Third, fourth, and fifth editions are refined editions that were designed. AD&D, before third edition, AD&D was just kind of cobbled together. Anyway, what are we talking about? So the best thing to do is whatever it occurs to you to do. Some notes. So the form of a rational function is to be a polynomial over a polynomial. Rational functions are to polynomials as fractions are to the natural number. The zeros of Q will produce either holes in the graph or vertical asymptotes. Zeros of the denominator will produce holes in the graph or vertical asymptote. Holes in the graph happens when a factor cancels out, like, completely. You get a nice little hole in the graph when a factor cancels out. If the factor doesn't cancel out, you end up with a vertical asymptote. Prosecution will stipulate that y'all know how to factor. So I'm just going to go with the factored form so you can see very clearly what's going on. I got a polynomial over a polynomial. We can see that the x minus 1 cancels out. So we'll have a hole in the graph when x equals 1, and we'll have a vertical asymptote when x equals -3. In the context, so what we see about this function is that this function will be discontinuous when x is equal to 1 and when x is equal to -3. We can see that the limit when x is equal to 1 is just going to be 3/4. Did I write 2x plus 4? Oh, 6/4. Because I can plug in the value after I cancel out the 1, the x minus 1. But the limit as x approaches -3 does not exist. Vertical asymptote, limit doesn't exist. Hole in the graph, as long as both sides are headed to the same place, which they will be, in this case, we just plug the 1 into the rest of it. So 2 times 1 plus 4 is 6, 1 plus 3 is 4. So 6/4. Any questions? Is everybody okay? Moreover, since the vertical asymptote at x equals -3, since that factor that made that asymptote x minus 3 has an odd exponent, that means the two sides go in opposite directions. One side will go towards infinity, the other go towards -infinity. If it was an x minus 3 squared, then that makes everything positive and both sides will go the same direction. Either both sides go towards positive infinity or both sides go towards -infinity. For our purposes, we just need to identify that there's a vertical asymptote there, the limit doesn't exist. How's everybody okay? Calculus easy enough so far? I think it is. But then I've been doing calculus longer than most of you have been alive. Probably longer than all of you have been alive. That's not a brag, that's just a statement of fact that I am old. That's all. All right. One more thing to do today. One more thing to do today. We got to look at limits at infinity. Once we get the hang of this, we could think of this as how we can plug in infinity. This is evaluating a function at infinity. Now that statement flat out doesn't make any sense. You can't plug in infinity. It is not a number. So you do the calculus thing. It's like, oh, well, what is f of infinity? And the math teacher will be like, oh, that doesn't make any sense. What are you talking about? Then you roll your eyes and go, ugh. What's the limit as x goes to infinity of f of x? And the math teacher will be like, oh, that's better. That's only math teachers that are overly pedantic, like more likely. So the limits that we're talking about here are things like the limits as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. What we're looking for here are horizontal asymptotes. Our strategy is very simple. We approximate plugging in infinity by plugging in very large numbers. Nope, bigger than that. Nope, larger than that still. We're going to think about plugging in large values of x. That's why it's okay for me to be like, oh, turning to page, notes page 2. And you're like, oh, dude, there's only 5 minutes left. I'm like, oh, don't worry. We got this. We're just going to plug in large values of x. Let's look at an example. Let's think about the limit as x goes to infinity of 5x minus 7 over 2x plus 3. When x has a small value, that minus 7 and the plus 3 are pretty important. When x is only 1, that negative 7 is a big deal. So we have 5 times $1, and you owe someone $7. Ugh, that's negative $2. That negative 7 was a big deal. The larger x gets, the less important the negative 7 becomes. For large values of x, the only thing that matters is the 5x. That's one of the ways that we're going to think about it. For large values of x, the minus 7 doesn't matter. Large values of x, the minus 7 doesn't matter very much. Anybody here an accounting major? You might want to apply this kind of thinking, because the minus 7 is always going to matter. Bottom line of the balance sheet is $1.4 million. Excuse me, that's $1.4 million and $7. Don't think like an accountant. Think like a mathematician. Imagine this: when x is $1 billion, and I hand you a bag with $5 billion in it, you don't care that you're gonna have to spend $7 in gas to come pick it up. $7 doesn't matter in the face of 5 billion for large values of x. On the denominator, for large values of x, similarly, the plus 3 doesn't matter. For large values of x, the +3 doesn't matter. So the only thing that matters is the 5x and the 2x. So our thinking is that this is going to be the limit as x goes to infinity of 5x over 2x. So now we're just looking at a ratio of 5 billion divided by 2 billion, because those x's are going to be the same. We can get rid of the billion, and this is headed towards 5/2. For large values of x, the only thing we're going to care about are orders of magnitude. I just realized I should do one more, just real quick. In this example, x squared plus 5x plus 7. Now, with that x squared in the numerator, not only the -7 does not matter, the plus 5x doesn't matter. When x is 1,000,000, 5x seems like a big deal, but the 7 isn't. But if x is 1,000,000, x squared is 10 to the 12th. And when you have 10 to the 12th dollars, you do not care about $5 million. It is insignificant. If you are a billionaire, a few $1,000,000 doesn't matter. Doesn't change anything at all. However, the denominator has only got that 2x. So we look at what's important. The thinking is, what's the only stuff that matters? So for large values of x, this is still headed off towards infinity. The limit doesn't exist, but we're going to indicate that we understand where things are headed. This is why it doesn't exist. Yes. Correct. You care about degree and the leading coefficient. If the degrees are the same, it's the ratio of the leading coefficients. If the degrees are different, if it's infinity on top, the limit goes to infinity. If it's an infinity on the bottom, what would the limit be? 0. And at that point, we could say equals 0. Approaches infinity equals 0. 0 is a number. 0 is okay to have it equals next to it. All right. Oops, a little bit of overtime. I owe you 3 minutes of overtime. So since you're paying me, that's going to cost you extra. Actually, let's not implement that plan. That would be horrible. I should be paying you anyway. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.